Hi, in this video we are going to discuss about the dimensionality reduction technique. Firstly, we will go with what is the dimensionality reduction. Then we will discuss why we need the dimensionality reduction technique. Then we are going to discuss different approaches for the dimensionality reduction. Okay. First we will start with why we need what is dimensionality reduction. For suppose we have data with the d number of features f1, f2 is the d number of features. This we will convert into the d dash dimensional. Here d dash is going to be less than d. f1 dash, f2 dash, f3 dash, like this fd dash. Okay. Here d dash is going to be less than the d. Why we need this dimensional reduction technique? Okay. We by doing the reducing the dimensional reduction, we will reduce the dimensional. That means number of features we are going to be reduced. By reducing, we are going to reduce number of calculations, and also we are going to reduce the time taking. And the second most important thing is in the some algorithms is a distance based algorithms. When the dimensionality increases, we are going to get the problem of curse of dimensionality. We are going to face the curse of dimensionality problem in the KNN logistic regression only when we are using the distance based approaches. At that time we are going to face the curse of dimensionality. It because of the higher dimensionals. To avoid this problem, it's need to reduce the dimensionality. Okay, these are the why we need that dimensional reduction technique. Let's see some techniques. Okay, there are basically we are going to discuss two techniques. One is PCA, another one is TSNE. In this video we are going to discuss about the PCA, and the next video we will discuss about the TSNE. TSNE is the deep learning approach. Yeah. Now see the PCA. PCA is a principal component analysis. This is one of the statistical approach to reduce the dimensionality. Okay. To get more clarity, let's go with some intuition understand. Then we will deep dive into the mesh to get more clarity about the PC. Here we consider the two-dimensional data to get to make more easy. Okay. Here the f1 and f2 is the two feature columns, and this is the data that was when we plot. It was look like this, suppose. And here one thing we can observe that data is more spreading in the f2 and the spreading is f1 is very less. The spreading in f2 is this much. Okay, and the spreading is less. That means if you know the f2 values, we can store the maximum information of this data. Okay, spreading is more, we can store the maximum information by that feature that you got now. The spreading is more, that mean here the variance is going to be more. That means the future f2 has, we will get maximum variance, more variance compared to the future f1. Variance of f2 is greater than the variance of f1. Okay, how we'll get this one? If you suppose if you plot this one, the f2 is might be look like this. F1 will be very narrow. It was look like this. Okay, it was represent like this. Here also we can plot. We'll get the data is like this. Okay, and for this it's very thin. Let's see another case, how we can handle that case. If the data is look like this, here we can observe the variance in the F2 and variance in F1 is going to be maximum. That means it's more equal. Variance of F1 and very almost close. But here I want to convert this two-dimensional data to one-dimensional. How we convert this one? For suppose if you rotate this axis, okay, by rotating we will get the axis like this, F1 dash, and this is the F2 dash. Here we can observe that by rotating these features we will get the F1 dash and F2 dash. Here the F1 dash has maximum variance compared to the F2 dash. By taking only F1 dash we will get the maximum information. That means variance of F1 dash is greater than variance of F2 dash. And by taking the F1 only we will reduce the dimensionality. That means we have F1, F2 is the features that we have in the data. By shifting the axis we will get the F1 dash and the F2 dash. And here we observe the F1 dash is maximum variance. We will consider only F1 dash here. Okay. Initially we have two-dimensional data. Now we will convert it into single dimension. But how we can get this F1 dash is the most important thing. For that we will see the calculations of PCA to get those things. Yeah, I redraw the data here. Here also it was F1 feature and F2 feature. The data was look like this. Okay, and we need to find this direction F1 dash. For this I was drawn this one, and I will assume there is a point. This point I will consider that xi bar, xi dash. Each point we can represent with xi, and we are going to find the direction. This is the direction we are going to find. This is the direction we are going to find, and let's consider this one as unit vector u1. Now we will project this xi on u1. By projecting we will get the xi dash. Xi dash equal to the projection of xi on u1. We already know, we assume u1 is the unit vector, and we our goal is to find the direction of this unit vector. That is the thing. We know the projection of xi on ui. Just u1 transpose into xi dot and u by u1 more or less. Because of its unit vector, this value is going to be 1. Finally, we will get u1 transpose into xi. We have xi bar is equal to u1 transpose into xi dot product or unit. We are using transpose, that we can multiply that. And similarly for the mean point, we will just xi bar is equal to u1 transpose into x bar. Okay, all the points, one point this one, the mean point this one, we will get the mean. Now this is the direction having maximum variance. Now first we will find the variance, then we will find the maximum variance direction. The variance of projection of xi on ui, okay, that is equal to variance of u1 transpose of xi. The variance of u1 transpose xi is equal to the, we already know the variance formula, variance equal to 1 by n sigma I equal to 1 to n xi minus x bar whole square. Now similarly here also xi is this one, x bar is this mean. Now 1 by n sigma I equal to 1 to n xi dash minus x bar dash. Now place these values, I equal to 1 to n, we know this value u1 transpose xi minus u1 transpose into x bar, we got this one. Now we already know in the pre-processing step we are going to do standardization. By doing standardization we convert the data to normal distribution with mean equal to 0 and variance is going to be 1. This is the mean that we will get, this is equal to this. Okay, now this whole value is going to be 0. Sorry, here we have to get the square, forget that one, sorry. And finally we are going to get variance is like this, u1 transpose xi whole square. Now we need the maximum variance direction. Okay, the maximum of use the direction of the vector I need from the variance sigma I equal to 1 to n use a transpose xi whole square. This is the final equation. Now we have to solve this equation. By solving this equation we will get the unit vector uses. These unit vectors is also called eigenvectors. Here by solving this equation we will get the eigenvectors. Okay, now let's see how we can get those things. For suppose we have a data x and it contains the d number of features. Let's write this one into matrix form. F1 F2 is Fd. Let's consider like this. Okay. Now we are going to find the eigenvalues to this matrix. We already know how to find the eigenvalues. We are already studied this one in 12th grade like that. We will find the eigenvalues like lambda 1, lambda 2. We will represent the eigenvalues with the lambda and lambda d because we have d number of features. And for these eigenvalues we will also get the eigenvectors. That's called v1 for the lambda 1. For the eigenvalue lambda 2 we will get the eigenvector v2. Similarly for the lambda d we will get the vd. For suppose if lambda 1 is greater than lambda 2, greater than lambda 3, greater than lambda d, for these every eigenvalues we are going to get the eigenvectors v1, v2, v3, vd. For suppose the data is our data is suppose like this, f1 and f2, okay, a two-dimensional data, and we have to get this unit vector, and we have to get that unit vector, and because of it is two-dimensional data, we will get the lambda 1, lambda 2, and for these two lambda values we will get the eigenvectors v1 and v2. The direction of ui is going to the maximum eigenvalue, okay, and that means if lambda 1 is greater than lambda 2, that means we will have v1 and v2, these vectors. The direction of u1 is the v1, okay, u1 is same as v1, and v2 that we will get like this one is a v2. Similarly, here we can apply this one to the higher dimensional. The lambda 1 represent maximum. If the lambda 1 is higher value, that represents the direction of v1, we are going to maximum variance, and lambda 2 is the second option for you, and this variance is smaller than the lambda 1 and higher than the lambda 3. This was going like this lambda d, and by this eigenvalues we also tell the how much information we are going to get and how much information we are going to lose. To know that one, if you only consider the eigenvalue lambda 1, then we will consider like this lambda 3 and lambda d. The numerator is which eigenvector value of eigenvalue of the vector that we are going to consider, and the eigenvalues of the vectors we won't consider. By taking this information, we get the information how much information we are going to get by taking that vector v1, the numerator vectors. For suppose if we get the 3/4, that means we are going to store 75% of information we are going to get. We are losing only 25% of information. Sometimes it is fine. If you want to get the more information, we have to consider more eigenvectors. That means lambda 1, lambda 2 by lambda 3, lambda 4, like this lambda d. By this way we will get more information we have to get for the vectors v1 and v2. We can neglect these vectors directions.